Okay, in this video I'd like to continue working through the homework number 6 for the physics class. And I started working through problem number 3. That's a particularly interesting one. Here we have a snowboarder who's got a mass of 68 kilograms, coasting up a hill, and that snowboarder's initial velocity up the hill is 8.8 meters per second. The hill is angled at 25 degrees, and the snowboarder comes to rest after traveling 7.5 meters. In question A, we're being asked what's the magnitude of their deceleration as they coast to a stop, and there's a hint that says that you can use a kinematics equation for this part. So let's just jump over and look at the math for that. Now I've already written a bunch down here, but let's just try to focus on this little chunk here. So I've written down all the given information, taking note that the final velocity of that snowboarder was 0 meters per second. But in reality, we have the snowboarder that's coasting up a hill, so we have this slant that's occurring here. But the clue kind of gives us some information here. If we consider, let's see, I don't know if I can capture all of this. If we consider just the fact that the skier is moving forward on that slant, and just to change our perspective a little bit, you might recognize that we could use just a positive and negative sign for forwards and backwards. Because as the skier comes to rest while moving on that hill, it doesn't matter that they're at a 25-degree angle. It's just forward up the hill, and the deceleration or the acceleration vector is pointing down the hill, or backwards, the opposite direction. And so that's what that hint's trying to tell us. We can ignore the angle here and just think forward up the hill and backward down the hill. Since that's the case, since that's the consideration here, we can just use one of our old kinematics equations from last unit. And so this kinematics equation, I think, is appropriate. Final velocity squared is the sum of initial velocity squared and the product of 2 times acceleration times the displacement. We can isolate for A with a little bit of algebra, and then substitute our quantities in place. So our final velocity, of course, being 0, it's helpful to note. We had an initial velocity of positive 8.8, displacement of a positive 7. So in the act of executing this arithmetic here, we see a result of negative 5.16. And that's good. We wanted to see a negative sign here because the direction of the acceleration vector has to be the opposite of the velocity vector in order to obtain this deceleration in the straight line. Off to the side, I double checked my units. So we had a meters per second squared after subtracting these units above. So meters per second quantity squared. And in the unit below, we had a meter. So a pair of the meter measurements cancel out, and we're left with meters per second squared and acceleration. Now, when we look at part B, this one's kind of interesting. Now we do have to account for the angle. What's the magnitude of the friction force acting on this skier during their slowdown? Okay, so now we get into some interesting stuff for this particular unit. And back to the diagram here. So if I revisit this diagram, I do want to kind of clarify the way I've drawn it here, and I need to make a couple updates. Showing this free body diagram where this dot represents the skier, and all of these solid arrows are forces that are acting on the skier at any given time. Now, I had a rightward or a forward-facing vector to kind of describe the motion that was occurring in problem number 1, but there really is no net force pushing this skier forward anymore. The forces that are acting on the skier are effectively twofold here. Number 1, we have a frictional force that's pulling this skier backwards. I'm going to use a blue ink just to make this stand out. So we have a frictional force that's effectively pointing backwards, fighting against the skier's inertia. And then we also have this parallel to the surface force. I'm marking that with F, parallel, down here. And the sum of those two are equivalent in length to this red vector that I drew originally. That red force vector is the force vector responsible for generating the deceleration that we had in part A. Now, to be a little bit more clear, the skier is experiencing a weight force. That's what this black vector is showing here. Because this skier is here on Earth, we have a weight vector, the force due to earthly gravitational acceleration acting on the skier. And so I'm showing that in a solid line because that's the vector, that's the weight vector of the skier. And I've decomposed that vector into its perpendicular value and its parallel value. We can demonstrate any diagonal vector, and again, if you change your perspective, you'll see this as a diagonal or the hypotenuse of a triangle. But we can represent that diagonal vector as the sum of two perpendicular or component vectors, and that's what I'm showing here. I'm showing them in a dotted line because I don't want you to think that this pair of vectors down here is also acting on the skier. I'm just showing that that's an alternate way to represent this solid line. Now lastly, we have this vector that's acting on the skier as well. This is the normal force vector from the hill supporting the weight, if you will, of the skier. Now because we're on the hill, the normal force, and I should have drawn this a little bit more carefully here, this normal force vector is not as long as the full weight force vector, but it does need to be the same length as the perpendicular weight vector. So the notion of this normal force is that it's always perpendicular to the surface on which the object rests, and its job is to prevent that skier from either falling through the packed ice or producing any motion in this direction. It would be vertical if we were on a flat surface. Okay, so we can talk more about that in person if that explanation doesn't make a whole lot of sense, or you can do some research on your own. But this is essentially the free body diagram that we're faced with. We've got three vectors that are acting on this, and the, if you want to call it vertical vectors, are equal and opposite to each other, so we have no vertical motion. Hopefully you can see my cursor moving here. There's no motion in this direction because the forces cancel. There is a net force backwards here, and that's what's generating this backwards acceleration. So again, with that in mind, I'm just going to use a dotted line here. This first dotted line vector, this is again the weight force that's parallel to the surface on which the skier is riding, and then the second vector adding together to make this total reverse vector here, or reverse force. This is our kinetic friction force. So the way I would show that with math is something like this. We're going to go back to our Newton's second law definition here. The net force acting on an object is equal to that object's mass times acceleration. We're going to note that the weight force of the skier that's parallel to the surface on which the skier rides, so I'm using FW parallel here instead of just F parallel. That might help make some sense of this. Plus the frictional force, those are the two forces that are acting in that direction to produce movement on that skier. We can isolate the frictional force by subtracting FW parallel. And then side note again, the weight force that's parallel is effectively the solution to this side of the triangle. Now, if we're skiing up a hill at 25 degrees and I draw this triangle here, which is similar to the sketch that I've shown here, it's geometrically similar, so I know the angle in this corner is equivalent to the angle of the hill. The side length that I'm looking for, this parallel force, is opposite of the angle measure. We have the hypotenuse being the weight vector, so I'm using sine to isolate that. Now that vertical weight vector is simply the product of that skier's mass times earthly gravitational acceleration. So we're in pretty good shape right now. I think that formula is pretty straightforward and something that we can work with. I'm going to substitute in the mass and the acceleration that was experienced in that direction from the last step, and the mass, earthly gravitational acceleration, and sine of the angle measure. Now at first glance you might think that this is a typo or a mistake that I've made here. I've written 205 degrees instead of 25 degrees. And the reason for that is because I don't really want to spend the time worrying about when we're adding or subtracting vectors. I want to let the angle measure speak for itself. If we use the angle measure, point it in the direction using a unit circle reference, then that'll account for positive and negative components combining together. Now, in my mind, I'm thinking that this force should be negative because it's pointing backwards relative to the skier's direction of travel. But if I use the number 25, then sine's going to compute out to be a positive number. So all that I've done here is I've imagined what 25-degree angle in this direction would be on a unit circle measure. So 25 degrees below this horizontal is 25 degrees more than a 180-degree rotation. So if this 180 is combined with 205, I'm sorry, with 25, then I get 205 degrees. So, well, that's all that I'll say for now. We can talk more about that in class if we need to. The end result came out to be negative 68, which is again a good signal to me. We had a backwards kinetic friction force acting to slow this rider down, the snowboarder down. Double checking my units over here, kilograms times meters per second squared minus another kilogram times meter per second square. Don't forget that the result of a trig computation, standard trig computation, produces a ratio, side length ratio, and that ratio has no units. So kilogram meters per second squared is another name for newtons. Newtons subtract newtons to produce newtons as the result. So I'm pretty happy with this answer here. This seems reasonable to me. Finally, part C, what's the coefficient of kinetic friction between the snowboarder and the snow? Well, again, the kinetic friction force is equal to some kinetic friction coefficient times the normal force that's experienced by that skier. So the normal force is the force perpendicular to the surface on which we ride. So in this case, that perpendicular force is this side length of the right triangle that I've shown here. And in a similar way, we can find this perpendicular force by using trigonometry. Since that's adjacent to the angle measure that we've indicated here, then we ought to use cosine. So in part C, the work that I'm showing here is that the frictional force, the kinetic frictional force, mu k times F perpendicular. I could be more specific here, the force of weight perpendicular to the surface. That's our mg times cosine theta. So when we substitute values in, I know I've written down the negative 69.0 because that's the answer that we provided back here. But in my calculator, I actually copied this, this decimal. I could have gone all the way back and copied the entire expression that produced that decimal. And I kind of like that trick because it gives us a real precise answer, and it doesn't really violate our significant figure rounding issue. If I just use 69.0, we've already rounded, actually, yeah, okay, I got that right. We've already rounded this number and we've lost a little bit of accuracy. So if I use a rounded number in a future computation, that presents the possibility of more mistakes. So if you'd like, instead of using the 69.0, use the entire decimal because that effectively replaces this whole expression, then that would be totally fine. And then when we report our answer with extended decimals, like I've done here, we could then retain the, in this case, 3 sig figs and trust that this result is accurate to those 3 significant figures. A quick double check of the units on the right-hand side. Newtons are being divided by kilogram meter per second squared, which are also newtons. The unit Newton divides by Newton to effectively cancel out, and that's good for me because the mu value also is a unitless measure. It's more or less a ratio. So there's a lot to digest in problem number 3. There's a lot going on there. I'm going to go ahead and stop this video here, and then if you've got specific questions about it, please let me know. Thanks.